Welcome back. So we continue with chapter 1 and we move now to section 1.2 about open sets and related concepts. I will split this section into two videos because it's a lengthy section and it contains a lot of concepts and jargon. So in this video, I'm going to define the notion of an open set, an open subset of a metric space, the notion of the interior of a set, and the notion of neighborhood of a point. Okay, and in the next video, I'll talk about closed sets, closure of a set, the boundary of a set, and characterization of the closure of a set. Okay, so what are open sets? Okay, the notion of an open set of a metric space is a generalization of the notion of an open interval or an open subset of Rn, n-dimensional space. Okay, where does this terminology come from? Open. Why do we call such set open? Okay, most probably this comes from an analogy with a situation in real life. For example, when you say that a container is open, what do you mean by that? Probably you mean that it has no cap. Okay, so you can think of the cap as being the boundary of the container. Okay, now we will define precisely what do we mean by boundary later, but because we need first to introduce the notion of open. But let us keep things a little bit intuitive here. So let us say that a set is open if it does not meet or contain its boundary. Okay, so think of the open interval 0, 1 with endpoints removed. Okay, it has a property that if you take any point in that interval 0, 1, call it x, then all numbers around x, if they are sufficiently close to x, will still be in that interval. Okay, because there is I can always insert points between x and 0 and x and 1. Okay, so there's a whole interval around x contained in the interval 0, 1. Okay, and this is the idea behind the notion of open set. Okay. Why are we interested in such sets? Okay, there are many reasons, but I will present just one of them. If you look closely at the notion of the derivative of a function, let us say from a subset of R into R, f need not be defined everywhere. It has some domain. Okay, the definition, so the derivative of f at the point x in the domain is the limit of this ratio, Newton's ratio, f of x plus h minus f of x over h as h tends to 0. Okay, if of course the limit exists. But if you look closely, this requires that x plus h, at least for h small, this requires that this number, this increment, should belong to f, to the domain of f, in order to talk about f of x plus h. Okay? So the requirement is that there should be a certain number r such that if the absolute value of h is small enough, so it's less than r, then x plus h belongs to the domain of definition. And the situation is similar. We have a similar situation when we define partial derivatives or the total derivative of a function of several variables. Okay, here the domain of the function is a subset of Rn, of n-dimensional space, if you have n variables. Okay, so here's the requirement. If f is differentiable, then at every point on its domain, then the domain should satisfy this property that I talked about, that for every point in the domain, there should be a small number r, such that if h is close enough to 0, is small enough, so let us say norm of h less than r, then x plus h is in the domain. Okay? Now I can rewrite this condition by saying that for every x in the domain, there should be some number r, such that if whenever y is at some distance, whenever the distance between x and y is less than r, then y is in the domain. Okay, here I take any norm on Rn. Okay, and I can rephrase this condition by saying that for every x in the domain, there exists a ball of center x totally contained in the domain. Okay, now you maybe encountered sometime you can talk about differentiability of a function which is not defined on an open interval. For example, you may say that f is differentiable on a closed interval ab into R. But here one should be careful. What do you mean by that? Here we talk about the left derivative. Okay, we cannot define the right derivative because if h is positive, b plus h will be outside the interval, so it's not in the domain. Okay, so this is a particular case when we can define differentiability when the domain is not open. But in general, one should be careful. In the one-dimensional case, it's not really difficult. Okay, we can always manage to define differentiability on a closed interval. But in general, there is another way to define the notion of differentiability of a function which is not defined on an open set. So if you have a function, let us say of several variables, defined on a subset A of Rn. So usually we say that f is differentiable on A if f can be extended to a differentiable function which is defined on a bigger subset O, which is open and contains A. Okay, this is the usual way of defining. Now there are other ways, of course, but I will not get into them in this small introduction. So usually the notion of differentiability is defined for functions defined on open sets. Okay, because of this idea that I explained. Okay, so now I move to the definition in the general context of a metric space, because in a metric space we have the notion of ball. Okay, so I take this as the definition of openness. Okay, so if we have a metric space X and a subset O of X, we say that O is open if whenever X is in O, there is a whole open ball of center X contained in O, right? So this is the idea that I was trying to explain. So in words, a set is open if whenever it contains a point, it contains a whole ball around this point. And also, as we said, a set is open if whenever it contains a point, it contains all the points that are sufficiently close to this point. So this is the idea, and this is an illustration. If you have a subset O, and we consider a point, here it's a two-dimensional picture. So if you consider a point X, if O is open, then we should be able to include a whole ball of center X. And the radius, actually, as you may notice, the radius of this ball is not unique, first, because if R is such a number, then anything less than R, any ball of center of radius R prime less than R will also do this, will satisfy this. So I can take any ball less. But the radius in general depends on X. So if I choose X to be closer to the boundary, then the radius of the ball would be in general smaller. Okay, here I took the biggest such ball. Okay, I hope this idea is clear now. And now I'll give some examples as usual. So as a convention, we always equip R with the usual distance. Okay, so when I say nothing, it means the usual distance. Okay, so as we started in the introduction, the open interval 0, 1 is open according to our definition. Okay, and I explained this in details in math 1106. Okay, with the picture. But however, the interval 0, 1 closed at 1 and open at 0 is not open. You understand why? Because 1, if I add, so 1 plus epsilon or 1 plus h, if h is positive, is not in the interval, no matter how h is small. Okay, so the condition of openness is satisfied for all points in 0, 1, but not for 1. Okay, and similarly, all open intervals are open according to our definition. Okay, so the open interval AB, the open interval A plus infinity, the open interval minus infinity A are all open according to our definition, and I explained this in details last semester. Okay. Now, remark, very important remark. We know that the open ball of center X and radius R is contained in the corresponding closed ball, and the closed ball of center X and radius R over 2 is contained in the open ball of center X and radius R. Therefore, the condition of openness, it's a condition, okay? Not all sets are open. So the condition of openness is equivalent to this one. For every X in O, there exists a closed ball of center X contained in O. So in the condition of openness, I can put open ball or closed ball, doesn't change anything, okay? So there must be some ball. Okay, of course, because B prime is bigger. So if B prime is contained in O, then B is contained in O. And conversely, if BXR is contained in O, then B prime XR over 2 is contained. So I change the R, right? So this should be straightforward. Now, the first result, which is not a surprise, is that an open ball is an open set. And here, usually students may be confused because they may think that this is just a tautology. So we have to prove something here. It's not, it's almost trivial actually, but we have to write it. So this is not a tautology because an open ball is what, by definition, is a set of this form. So it's the set of points whose distance to the center is less than R. This is by definition. And an open set is a subset satisfying the condition of openness. Okay, so not quite the same thing. Okay, they are related, but we have something to prove here. So we have to prove that a set of this form has the property that I stated, has the openness property. Okay, and now things will become clear with the picture. Okay, so we consider an open ball BAR of center A and radius R. Okay, we have to prove that this set satisfies the openness condition. So I consider an arbitrary point X, okay, in the ball, in my set BAR. Okay, now it's clear on the picture that I can always insert a ball, another ball, okay, of some radius inside the bigger ball. Okay, this is the idea. And now here in the picture, I drew the biggest such ball. So a ball which is tangent to the first one. Okay, so I took the maximal radius possible. Okay, now what is the radius of this biggest ball? If the distance from A to the boundary is R, okay, so draw a radius here, then the distance from X to the boundary will be just R minus dxa. Okay, this is the biggest possible number that I can take. So if X is in BAR, the distance, by definition, the distance between X and A is less than R. So R minus dxa is strictly positive. So this will be taken to be the radius of the ball of center X. And now we shall prove that the ball of center X and radius rho, pictured here in blue light, is contained in the original bigger ball. Okay. Now, of course, pictures are very important in topology, but they do not constitute a proof because intuition may mislead us sometimes. Sometimes we accept a proof by pictures because writing a full proof, a rigorous proof, can be difficult. But here it's very simple to prove without looking at the figure why this ball of center X and radius rho is contained in the original ball. So how do I prove that? I take an element here and prove that it's here. So I take an element Y in the smaller ball here in light blue. So what does it mean that Y is in the smaller ball? It means that the distance to the center X is less than rho, which is R minus dxa. And therefore, when I add dxa, I get dxa plus dxy is less than R. But now, by the triangle inequality, dya, the distance between Y and A, so take Y here, the distance between Y and A is less than the distance the sum of dAx plus dxy. Okay, so this quantity here is less than this quantity, so it's less than r strictly, and therefore y is in VAR by definition. So any element here is here, and therefore we prove the claim, and it follows from the claim that VAR is open. Okay, so any open ball is an open set according to our definition. Okay, now let us write some properties of open sets. If we have a metric space, what about actually the whole space and the empty set? The whole space is open and the empty set is open. Okay, this is not difficult to prove. I'll prove. And an arbitrary union of open sets is an open set. A finite intersection of open sets is an open set. Okay, here you have to pay attention to the adjectives. Here I can take any union. Okay, but in condition 3, I have to take just finitely many elements. Okay, and I will give you a counterexample now. Okay, why the empty set? The whole space is open. Okay, so I have to check that the whole space satisfies the condition of openness. So I take a point in X. Then any ball, in particular the ball of center X and radius 1, is by definition contained in the space. So this is trivial. So the whole space satisfies the open condition, and therefore it's open. Okay. Now the empty set may be more confusing. The empty set is open because I cannot find any point in the empty set, because the condition of openness tells me that if you have a point, then you can find a whole ball around that point. So if the assumption is wrong, then the implication is true, right? So we say that it's vacuously true. Okay, so the empty set is open because there's no point in the empty set. And if you find this reasoning not very satisfying, you can say that you can change a little bit the definition by saying that a set is open if either it's empty, okay, or for every X in the set, there exists a ball around the set containing in the set. Okay. So the whole space and the empty set are open sets. Property 2, an arbitrary union of open sets is an open set. Okay, this is also not difficult. So I consider an arbitrary collection O lambda indexed by an index lambda in some set L. And I want to prove that the union is open. So I have to check that the union satisfies the openness condition. How do I do that? I take X in the union, and I have to prove that there is a ball contained in the union, of center X contained in the union. So if X is in the union, then it is it's in one of them, one of these sets, call it O mu. Okay? Just pick one index to which X belong. And I know that O mu is open. So by the openness condition, I can find a ball of center X and radius R totally contained in O mu. But O mu is contained in the union, right? The union is always bigger. So the ball in particular is contained in the union of O lambda, and this is just the openness condition. Since X was arbitrary, the union is an open set according to our definition. Third condition, it's enough to prove that the intersection of two open sets is an open set, because if you prove it for 2, you can just do an induction. By induction, it's true for, you have to write it if you don't believe me. If you prove it for 2, then you prove it for any number, but the number must be finite, cannot be infinite. Okay? Just induction on the number. Okay, so why the intersection of two open sets is an open set? Okay, so consider two open sets, O1 and O2. We have to prove that the intersection satisfies the condition of openness. So I pick an element in the intersection, and I have to find a ball contained in the intersection. Okay, if X is in the intersection, then it's an O1, but O1 is open. So I can find some ball, let us say of radius R1 and of center X contained in O1. And similarly, since O2 is open, I can find another ball. So I cannot say that maybe the radius is different. Okay. So now I just take the minimum between these two numbers, and by set theory, the intersection of these two balls is contained in the intersection, because the first one is contained in O1, the second ball is contained in O2, so the intersection is contained in the intersection. But the intersection of two balls with the same center and different radii is just a ball. The ball will center the smaller one. Okay, this is not difficult to prove actually. So how do I prove that? If you don't believe me, if you just take R equal to the minimum, double inclusion if you like. If a y is here, then the distance to x is less or equal than r. Is less strictly than r. So it's less than R1 and less than R2. So a point here is here, and conversely, if the distance between x and y is strictly less than R1 and strictly less than R2, then it's strictly less than the minimum. Okay, and that's it. So we found a ball of center x, which is totally contained in the intersection, and therefore the intersection satisfies the condition of openness, and so it's open. Okay. Now, as I said, we cannot take any intersection. So an arbiter intersection of open sets need not be an open set. Here's the counterexample. If you consider this decreasing sequence of intervals of center 0, so -1 over n, 1 over n, okay? So as n get bigger, these shrink, okay? And you may prove that the intersection of all these intervals, what happens at infinity, is just the singleton 0. Okay, so this is double inclusion, because 0 is in each interval, so it's in the intersection. And conversely, if I take any element x in the intersection, it's between -1 over n and 1 over n for every n, and as n tends to infinity, I get x equals 0. Okay, so this is just, so the intersection of open sets, each such interval is open, but their intersection is not open. Okay, the singleton 0, as you know by now, is not open because, for example, if I add to 0 a small number epsilon or h, it cannot be in 0. So 0 is not open. The singleton 0 is not open. It doesn't satisfy the condition of openness. Okay, now we come to the notion of neighborhood, an intuitive concept. A neighborhood of a point x in a metric space is any set V which contains an open set that contains x. Okay, so, and the set of neighborhoods of a point x is usually denoted by calligraphy q of x. Okay, now we have to observe that the whole space is a neighborhood of x by definition, because the whole space is open. So in particular, actually, any open set containing x is a neighborhood of x. But here we just have to say, I have a remark actually. So first remark is that any set containing a neighborhood of x is also a neighborhood of x by definition, because, and I don't assume that any one of these are open. So a neighborhood, according to our definition, need not be an open set, but it contains a smaller open set. Okay, so if V is a neighborhood is a neighborhood of x, then V contains an open set O containing x. But since U contains V, U contains O, and therefore U is a neighborhood of x. Okay. So for example, the closed interval -1, 1 is a neighborhood of any point strictly between -1 and 1. Okay. Just take if you take x between -1 and 1, then this is an open set. Okay, so this is an open set containing x and contained in the space and set V, if you like. So this is not open, but it contains an open set containing x. However, of course, -1, 1 is not a neighborhood of 1. Okay, because I cannot find an open set about 1 or an open interval about 1 totally contained in this, because any open interval of center 1 would contain points to the right of 1. So it contains something like 1 plus epsilon. So cannot be contained in that. Same thing for -1. Okay, and just a remark on terminology. yeah, I'll do it. I will say it later. Now, first result, because there is not all mathematicians agree with this definition. Okay, so there are two definitions of the concept of neighborhood. Okay, we will follow this definition. Okay, so according to this definition, a set is open if and only if it is a neighborhood of all its points, and this is very useful in practice to show that set is open. Okay, so we take an arbitrary point in that set, and we find another open set containing the point and contain. Okay, so there are two implications here. If A is open, I want to prove that. So suppose that A is open. I want to prove that A is a neighborhood of any point in it. So take any point x in A. Okay, then by definition of so since A is open, we can write x belongs to A and A is contained in A. Okay, so this is really trivial. Okay, so A is a neighborhood of x. Right? So now conversely, if A is a neighborhood of all its points, now here it becomes more interesting. Okay, if A is a neighborhood of all its points according to our definition of neighborhood, what does it mean? It means that for every point x in A, I can find an open set O sub x, because it depends on x, right? That contains x and is contained in A. This is just the definition, okay? And this permits me to write A as the union of all these OX, where x varies in A. Okay, how do I prove such equality? Double inequality. It's really, I will not write it, but I'll do it orally. You write it, okay? So how do you prove this set theoretic identity? Double inclusion. First of all, you take an element in the union, okay? So call it, let us say, small a. Small a is in OX, so is in the union, so it's in some one of them. So if you take any element small a here in the union, it belongs to some OX, but OX is in A, so small a is in A. So this is one inclusion. Other way around, you take small a in capital A, then by definition, small a belongs to capital O small a, right? but OA is in the union, so small a is in the union. Okay, so almost trivial actually. So once we have this, we are done, because now OA is a union of open sets, but we proved that a union, an arbitrary union of open set is an open set, so A is an open set. Okay? And now I have to warn you about different usage of the word neighborhood. For some mathematicians, for example, for Mankris, for him, a neighborhood of a point is just an open set containing that point. So simpler, okay? The definition is simple. But if we take this definition, this proposition becomes a tautology, okay? Because we have nothing to prove here, okay? But the good news is that in practice, this is not a big deal, because we can always, when we reason about neighborhoods, we can always suppose that our neighborhoods are open, because if they are not open, we can take something smaller which is open. Okay, so this is just proposition 1.3. Okay, so now the last concept in this video, the interior of a set A. By definition, the interior of a set A is the union of all open sets that are contained in A. Now, the union of all open set is an open set, and it's the biggest one. So, otherwise stated, the interior of A is the biggest open set contained in A. And it's denoted by a circle above or and A. And here are some examples. This example, I proved it in last semester in M2201. The interior, and it's not a surprise, the interior of the closed interval 0,1 is the open interval 0,1. Let us review the proof quickly. How do I know that according to our definition? It should be intuitively clear actually, but here's the rigorous proof. Double inclusion. So first of all, the interval 0, 1 with endpoints removed is open and contained in 0, 1. But this is the biggest open set, so it contains 0, 1. Okay, so first inclusion, 0, 1 open is contained in the interior. Okay, so what do we have actually? So the interior contains, the interior that I don't know now, it contains the open interval 0, 1, and it's contained in the set, because by definition, so a circle is always in A by definition, because it's the unit of the biggest open set contained in A. So a circle is always in A. So I have a set now which is between 0, 1 open and 0, 1 closed. So what are the possibilities? Okay, there are not so many sets in between. So we have just 4 possibilities. Okay, either this set is 0, 1 open, or 0, 1 semi-open, closed at 1, or closed at 0, or the whole space 0. Now, which one among these is open? Just the first one. This is not open, this is not open, this is not open. So just we are left with just one possibility. So this is, so prove that the interior. And similarly, actually, the interior of all intervals of endpoints 0 and 1, no matter if they are closed or semi-closed, their interior is the open interval 0, 1. Okay. Next example, the interior of the set of rational numbers. Okay, so all these are subsets of R with the usual distance. The interior of the set of rational numbers is empty. How do I know that? Because, as we know, any open interval contains rational numbers and irrational numbers. Okay? And therefore, it cannot be contained in Q. Okay? So the only open subset of Q is just the empty set. Because if it had a point, then it would have a whole open interval around that point. But this is impossible. Cannot find a whole interval contained in the rational numbers. And for a similar reason, the interior of the irrational numbers is also empty. Okay, and similarly, the interior of the set of integers is also empty. Okay, same thing, because actually there are 2 ways to prove this. First way is that since Z is a subset of Q, then as you shall see, the interior of Z is in the interior of Q, so it's empty. Or we can do just the same reasoning, because I cannot find a whole interval consisting of only integers. Okay, it's not possible. Because between any 2 integers, I cannot find a third integer, for example. Okay. Now, and the last result is that a set is open if and only if it's equal to its interior, and this is something that should not be a surprise. How do I prove that? 2 implication. If first A is equal to its interior, the interior is by definition open. So A is open. Straightforward, trivial. Conversely, if A is open, then first A contains A, right? But A is open. Since a circle is the biggest open set containing A, then it should contain A. So we have a double inclusion. It's also trivial. So a circle by definition is contained in A, but it contains A. So we have equality. Okay. So that's it. So this is for the first video. In the next video, I'm going to talk about closed sets and related concepts. So thank you for your attention.